hope you are ready. There are two learning objectives to be achieved throughout this video. First, we will study how the change in concentration affects the equilibrium position according to Le Chatelier's principle. Second, we look at how the change in pressure and adding inert gas may affect the equilibrium position. Let us go through the first part of the lesson with my buddy, Mr. X, about the effect of concentration change.
Hey there, and welcome. You know, it's funny. Have you ever just stopped and noticed how everything, and I mean everything, from the economy to a forest ecosystem, always seems to be trying to find some kind of balance? Well, today we're diving into the chemical version of that exact idea. It's called Le Chatelier's principle, and we're going to focus on one specific part of it. What happens when you change the concentration? Or, to put it another way, the crowd size in a reaction. And to really get what we're talking about, just imagine this. You're at a party. It's great, the vibe is perfect, everything feels just right. And then, all of a sudden, a massive group of people walks in and crams into the room. That feeling, that sudden sense of, whoa, it's way too crowded in here, that is exactly what a chemical system feels, and it's the key to understanding this whole principle. So, before things get out of hand, let's talk about that perfectly balanced party. When a system, or a party, finds its natural, comfortable rhythm, we have a special name for that in chemistry. We call it equilibrium.
Okay, that sounds pretty technical, right? But stick with our party analogy. Imagine the party is spread across two rooms. Equilibrium is when the number of people leaving room A to go to room B is exactly the same as the number of people leaving room B to go back to room A. So even though people are constantly moving back and forth, the total number of guests in each room stays the same. That's it. That's chemical equilibrium.
And this is a really, really important point. Equilibrium is not static. It isn't frozen in time. The party is still very much alive. People are mingling, they're moving around. It's a dynamic, living state. But the overall balance, the crowd density in each room, just remains perfectly stable.
All right, so we've got our perfectly balanced system. But what happens when that comfy balance gets totally wrecked? What happens when you put that system under stress? This right here is the absolute heart of Le Chatelier's principle. So, back to our party. Imagine a huge new group of guests arrives, but instead of spreading out, they all decide to cram into just one of the two rooms. That's the stress. The party's immediate, natural reaction is to do whatever it takes to fix the situation, to spread everyone out and make things comfortable again.
Let's actually watch this play out in a real chemical reaction. Don't worry, we're going to keep our party analogies going the whole time so it all makes perfect sense.
So here are our chemical partygoers. On the left side, we've got nitrogen monoxide and oxygen. Let's just call them the guests in the reactant room. And on the right, we have nitrogen dioxide. Those are the folks in the product room. Now, check out this graph. At first, you see the reactant lines going down and the product line going up. But then, right at time t1, see how the lines go flat? That's it. That's our perfectly balanced party. The number of guests in each room has stabilized. We're at equilibrium. And here it comes, the disturbance. Look at time t2. See that sudden, sharp, vertical spike in the green line? That's our new group of guests crashing the party and piling straight into the reactant room. Instantly, the balance is shattered. That room is way, way too crowded.
So, what do you think happens? People aren't just going to stand there all crammed together, right? Of course not. They naturally start moving from that overcrowded room into the less crowded one to get some breathing room. And that's exactly what the chemicals do. The system shifts to the right, using up that extra NO to create more of the product, NO2. The crowd starts to thin out.
And by the time we get to T3, look at that. The lines are flat again. A new balance has been found. Now, the party isn't exactly like it was before. The number of guests in each room is different now. But the flow between the rooms is balanced once again. The system adapted to the stress. Pretty cool, huh?
So now that we've actually seen it happen, we can lay out some simple, totally predictable rules for how these systems respond every single time. Let's call them the rules of the room.
Okay, the logic here is actually super intuitive. Basically, nature hates overcrowding. If you add more stuff to one side, the system will immediately shift to the other side to try and use it up. And if you take stuff away from one side, the system shifts towards that side to make more and replace what was lost. It's really that simple.
Let's do a super quick example. If we dump in a bunch more hydrogen, which is a reactant on the left,
the system instantly shifts to the right to start using it, which means we make more of our product, HI.
And you guessed it, the opposite is just as true. If we were to somehow pull some hydrogen out of the mix, the system would fill that gap and shift to the left to produce more hydrogen and try to get back to that comfortable balance. But here is where it gets really, really fascinating. Because while all this shifting is going on and the amounts of chemicals are changing, there's one little secret, one special thing that stays exactly the same.
And this is it, a little something called the equilibrium constant, or Kc. So even though the actual number of guests in each room changed after that disturbance, the mathematical ratio between the two rooms snaps right back to what it was before. To put it back in our party terms, the number of people in each room is different now for sure, but the overall vibe of the party, that perfect ratio of guests to space, has returned to that same comfortable constant.
All right, let's lock all this in so you don't forget it. Here's your quick and easy cheat sheet.
Here's the bottom line. If you want to make more stuff, more products, you can either add more of your ingredients, the reactants, or you can scoop out the product as it's being made. Both of those things will push the system to the right. And if you want to go the other way, you just do the opposite. Simple. So I'll just leave you with this final thought. We just saw that these chemical systems, they don't break when they're stressed. They adjust, they shift, and they find a new way to be balanced, a new normal. So if nature's default setting is always to find balance, what could that teach us about how we navigate stress and change in our own lives?
Thanks to Mr. X for a brief explanation. Next, we look forward to the second part shared by another buddy, Miss A.